speed. This. The synchronous speed is dependent on the frequency and poles, number of poles. We can change the frequency when we change the NS synchronous speed. Also, we can change the poles, the number of poles. Some people think for an induction machine, the poles the count change, but use some special methods. We can change the number of poles. So this is the method, and also we know the speed. The speed can change if we change the sleep. We know the real speed of induction motion is 1 minus s, 1 minus s multiplied by the synchronous speed. So you can change the speed, also can change the real speed of the induction machine. How to change the speed? There are 3 methods. We can change the state voltage, we can change the rotor resistance, and also we can change. Also, we have a method named sleep energy recovery. We'll explain them in detail in the next slides. First, let us see an example. See this example. This is an easy example. Just a general introduction. The parameters are noted in red color. It's a 4-port lubricant, and we know it tells us that the rotor current is 6 times. So there are 3 problems to calculate the starting torque, and then slip and speed, and also calculate the maximum torque. So these 3 questions are based on the equations we have studied yesterday. That's the first our review of the solution. We know in this example we don't know the circuit parameters. It didn't give us the parameters, so we can't calculate them. Use the equations last week we have studied. Can't use these equations, but we have calculated we can use another method we have just learned yesterday. Let's see. First, anyway, we have calculated the synchronous speed. So it's easy. The pulse is 4, f is 6 hertz. So we can easily obtain the synchronous speed, and then to know the
Sleep.
We know the speed. The speed is 1007. Yeah. So we know the sleep and follow SL and follow to the sleep. And then we know we can calculate the followed torque because the torque can be calculated by power. The gap. This is the air gap. Ag. In some time it's used designated by the GH. Here the air gap divided by the speed, omega s. So because it's proportional, we know it's proportional to the rotor current square, and inversely proportional to the speed. So we can this is followed. So if we have similarly two equations, we can know the ratio of start torque and the followed torque, because it's proportional to this equation. So we can obtain this new equation. Here, then we can calculate the start torque. The 6 here, we know in the problems. Induction mode, 6 times the rotor current and followed, because the start current is 6 times the followed current. So the six numbers meaning is this. So here is the 6, and then we can obtain the result is 1.8 as followed torque. So it's generally we know yesterday the starting current is generally 5 to 7 or sometimes to 8 to 10, and here is just 6 times followed. The followed
starting torque equal 6 times.
That's 6 times and the starting torque is 1.8 times the followed torque.
Sir, you said we have an experiment.
Yes, another teacher. Met 2 weeks.
After 3.
But I don't know the arranged time.
Oh. Who is building that? Who is building? Where? Where?
This semester.
I mean, who is building? Like engineering building one?
Building what?
I mean, where we have this experiment?
What's the time?
I mean, place.
That is building one. Building one. There's some there's experiment lamps. It's another teacher.
이제 왜 상이 쓰이네?
But he didn't tell me the arrangement in detail. About 2 weeks.
하기 어제 거함스러워 지금
Okay. Okay. We know the torque the ratio of the general torque and the max torque. We have knowing this equation yesterday. Last week we also explain this equation. So we can just replace the T as T followed, and S replaced by S followed. The max is same, T max and S max. So we can get the ratio of the T start and T followed and T start. So these two equations. So then from these two equations, then all found T max. All found T max, but here is T followed, here is T start. From these two equations, we can get the new equations T start over T followed. It's a mathematical problem. So here the ratio number is 1.8. Also, the true answer is the same. So we can get the max sleep. We can get the max sleep from these equations. We can get max sleep square. Okay, we can get the 1.31. Okay, if we have the max sleep, we can calculate the speed and max sleep. Just this expression. So it's 100,000 meters. And the last problem, kind of from the previous question. T start over the T max. We use this equation because we have know the S max and we also know the T start, so it's easy to calculate. So the T max is about three times the followed torque.
T max 3.18 meters.
So this is a simple example how to calculate the maximum torque. If we don't know the parameters of the rotor stator R1, R2, X1, X2, if we don't know the parameters, we have another method, just this method, to calculate the values of the torque. Okay, this is the problem, and then we see this equation. We know this equation. The speed, the synchronous speed. So we change the speed. We can change the stator voltage. If we change the stator voltage, also the slip will change. And also the rotor resistance, it can also change the slip. And rotor voltage. These three methods to change the slip and then change the real speed. Also, we can change the synchronous speed distance by this equation. So we can change the frequency or change the pulse. So there are totally five methods: frequency, number of pulse, and this voltage and resistance. We have five methods to change the speed of motor speed. So first, let's see the first one. This is the first change the synchronous speed. Two methods: change F, change P, number of poles. Here there's a difference between these two methods. The poles, the number of poles, it's integer number. And two, four, or six. So it's a step method. But the frequency, we can continuously change it. So the speed vary the parameter continuously. So let's see how to change. First, how to change the pose. This is the figure. Shows the principle of how to change 8 poles to 4 poles. The connection between them it's the stator poles. The connection here is in series with but we change the connections in parallel with this method. So the poles is different. So here only have 4 poles. The current follow with the wires is different. So the flux, the mathematic field is different. So it has only 4 poles. This only the difference is series, parallel, series and parallel. It can change from 8 poles to 4 poles. Maybe use another time, another method. You can change the 4 poles to 2 poles. But it's complicated. The induction machine. It's a complicated connection, and it will be huge and expensive. So generally, we change from one number from another number, just two numbers of poles. Okay, and see this one. Okay. Another example. 4 poles to 1 pole. 2 poles. The method is a little different from the previous one from 8 poles to 4 poles.
4 poles. Sir,
This is 4 to 2.
how?
Just the connection. You can see the connection. So it's a delta.
Yes.
It's a delta connection in series with 2 windings. Series 2 windings. But we changed the connection here. So the out is a direct connection, but the terminal connected to the middle of
The neutral line?
the middle of the 2 windings, A, B, C, and also with connection the original 3 terminals in star. So this can so in this time there are only two poles. This can be determined by the Fleming rules. It's so complex. It's not a very practical method. It's not a practical way of controlling the speed.
Sir, how can we get 4 pole to 8 pole to 4 pole?
Yes, also, but it's complicated.
Can I see this diagram, please?
No, this
4 pole to 2 pole. I need to see 8 pole to 4 pole.
Yeah. Generally we don't do that.
Why, sir?
It's so complicated. We have another good method to change the speed. Another good method. This is not a good method. Just in the earlier times, people do this. But then we have the frequency converter.
So we know n equal 120 frequency over 4.
Yeah.
So if we need to increase our n, so n equal, we need to decrease our pole.
So the minimum number is 2.
Minimum.
Yeah. The minimum number is 2. 2 poles.
So if our poles number is down, our speed is going up.
Yeah. So the maximum torque, maximum speed
Is
is
pole number 2.
is for 2 poles. Yeah. 2 poles. So we see here, if we want to have more than two speeds, so more windings are required, and the machine becomes heavier and more expensive because the construction of the machine is complicated.
Heavy machine. Instead of bigger.
So an easy method is to change the frequency. Easy method just to change the frequency. And we know if we use this method, we know the torque of the induction machine. By this equation, we know the torque is proportional to the voltage square, and it's related to the speed. Use this equation, we can draw the curves. The torque speed curves. and different frequencies. Different frequencies. So this speed. So the frequency of omega it's not very clear. It's not very clear. Just the omega h. It's a ratio. It's a ratio between the two frequency. It's 1 time, 2 times, 3 times. So for different that frequency, there's different curves of different top speed curves, and there are different starting
point,
starting top. This is the starting top.
একদম 3 নাম্বারটা যে করতে মানে প্রথম রইল 1 নাম্বারের যে গ্রাফটা না এটা যে করতে ফার্স্ট থেকে হারিয়ে কি করার আগে বুঝে
Generally, we use this method by this figure. This is a three-phase source. We use a rectifier
inverter
to turn it to DC voltage, DC current, and then DC is converted to AC.
Sir, so why we don't use AC directly? Because first time rectifier.
Yeah, sometimes there's an equipment can directly turn AC to AC. Okay, it's also okay. AC to AC equivalent.
So why we use rectifier?
This is a general method. And it can change the frequency in a wide wide during. But AC to AC, the frequency is limited in a narrow frequency.
That rectifier and inverter they change this frequency.
Yeah, this is widely used. It can output the zero frequency. It's 0 to sometimes of the rated frequency. It has a wide.
My question is rectifier AC to DC and
DC to
AC. But our input is AC and output is also AC. So why we use this rectifier and inverter?
So the frequency is different. Here is 60 or 50 hertz.
Yes,
constant.
Yes.
But here the frequency can be changed. Maybe 40, maybe 30, maybe 2, maybe 10.
Only for frequency changing.
So it can continuously change the frequency. So here the frequency is any value here. So the frequency any value you want to set it can output maybe a 10 hertz maybe a 10 hertz three-phase source. So the speed can up and down. Because this AC and this AC, the frequency is different. If the frequency is constant, the frequency can be changed or any value.
20, 30, like.
So let's see the three equations about the maximum torque, development torque, the start torque. We can notice that when the frequency increases, the torque decreases. Yeah. You see there, the frequency 1, 2, 3, 4, 5. For the 5 one, the frequency is it increases maximum, but the torque is low. The torque is low. Sometimes we don't. It's not designed. Designed. We want high frequency and high torque. But use this method, the torque decreases. How to solve this problem? We use another method. We'll explain next slide. Here, I will tell you is that we know the state flux. State flux is proportional to the ratio of the voltage and frequency. So if we decrease the frequency, while keeping the voltage high, we can get this curve. But if the frequency and the voltage, the ratio between them is constant, the curve is different. So generally we vary the voltage and the frequency. We vary the voltage and the frequency at the same time. So if we decrease the frequency, we also should decrease the voltage. So this is called VF control.
Voltage and frequency control.
It's generally method. We call it VF control. If you increase the F, you should increase the voltage. Use this method, we can get the curves of the torque speed curve, showing in this figure. So use this method. We can control the speed of the motor, keeping almost the slip and the maximum torque. The slip and the maximum torque. It's only changed a little. So use this method, we can get the maximum torque and speed as we want. So this method is better than this method, only changing the frequency. If we only change the frequency, so the torque characteristic is not very good. We don't want this. But if we change the frequency and also at the same time change the voltage, the curves this curves are better. We can get a larger torque, starting torque. Okay, this is the method of changing the synchronous speed. And also, the third method is to change the state voltage. We know the torque is proportional to the voltage square. So if we decrease the voltage, and the starting torque will decrease too. So with high 1.0 voltage, the starting torque here, but 1.5 voltage is the lower voltage. It's a lower voltage induced a lower starting torque. So it's the drawback of this method. Okay. The method is just use. You can think this resistance just as it's a continually varying switch. It can change the voltage to the machine. Let's see the fourth method. The rotor voltage control. It's also called the sleep energy recovery. Here is the method of and resistance. External resistance is to the wound rotor synchronous. Yesterday we have learned this method about to start the motor. And also we can use this method to control the speed. The advantage is that this method is simple. And we can get high torque. The disadvantage is that the efficiency is low. As a control speed, it's a slow control. It might take more time. To change the speed. Okay, and another alternative method of varying the rotor circuit resistance. We use special circuit we call the three-phase diode bridge. In this case, some of the energy is extracted from the rotor and displayed as heat in the resistance of external resistance. So also, this method is low efficiency. Can use this method. So here is the rectifier, here is the inverter. Use this method, we can increase the efficiency because there's no losses. This time there's losses in the resistance. But this method, the power will back to the grid. So we change the speed and also the power back to the grid. So the efficiency, we can increase the efficiency. So in general, the efficiency is
1 minus S.
Minus S. If the S increases,
decreases is
down.
down.
Yeah. So this is general conclusion. So at last, the most efficiency method is changing the voltage, and change the frequency. We call it is the third method is the VF method. So VF method is widely used in many industrial applications. So the file method, then change the frequency. Also in this method, we change the voltage together. This method is the best. Is the good one. The good method. Other methods we use less. Okay. Take a break. Induction machine. It's a single phase induction motor. Generally, it will be used as a motor, and not used as a generator. Yeah. So it's usually a motor. So we see that the small single phase induction motors are used in many household appliances such as blenders, juices makers, vacuum cleaners, washing machines, refrigerators, air conditioners. So they all are single phase induction machine. Generally, just like a 3-phase induction machine. So it also has the stator and rotor. So but there's we see here. We call it the single phase, but it's truly a 2-phase. It's truly a 2-phase. Yeah, it's 2-phase because it has two wires. This is starting winding. This is main winding. It has 2 windings. We'll explain the starting principle of the single phase in other slides. In general, the single phase motor is squirrel cage. So how can it? We know the single phase source count generated the rotational flux. If no rotational flux, but how it can rotate? We have this theory. It's double revolving field theory. This is base. This is the base of the single induction machine can rotate. It's easy to understand, and we also have a video to explain it. The basic principle is that we see this figure. In this figure, the single phase motor, main winding, the main winding can be seen as two rotating fields. One is clockwise and another is anti-clockwise. It's just the same as two rotating flux. The two rotating flux at the same speed. just the direction is different. So the torque is balanced. So it can't rotate if in standstill, if the machine is in standstill, it can't rotate. But if you push it, it can move. Then the torque is not balanced. Then it can rotate.
What percent?
There's two sleep, positive and negative. Just can understand it, is okay. Just can understand it. There's two sleep, and then we see this. We should also understand the simple equivalent circuit. And some parameters of the circuit are the same with the three phase of the superseding induction, except the slip, no slip. Let's see that. This thing. Let's figure. This is rotor. So it's just similar to the three phase equivalent circuit. A little different. There's two rotational field, clockwise and anti-clockwise. So there are two circuits in series with. Just
Why this is divided by 2? The X stator what 2,
yeah.
other stator what 2.
The flux can be explained as two rotational flux. So two rotational flux use the two equivalent circuit.
So this is divided by 2.
Yeah. Just see some power flow. This input power flow. Input power is just the voltage multiplied the current, and this is power development power. Okay. And this is the curve. The character curve. This is the speed. This is torque. So we know that there's a maximum value. There's maximum value of it. So this from here to here is the stable operating region. So it usually works. From this speed to this speed. And we should know the starting top. How to start the single phase motor. And start if the single motor is standstill, so the torque is 0. It can't rotate. Because it has the power setting single magnetic flux. We have learned this flux in chapter 4 of our textbook. Before the rotational magnetic flux. So it can be generation of two rotating magnetic flux, one clockwise and one anti-clockwise. So if we want to start it, so we should have another winding, another winding. So we have the starting. This is the starting winding. This is the main winding. The two windings, the angle between them is 90 degrees. So if it is 90 degrees, it can generate the starting torque. Then it can rotate the speed. So this is the method of starting the single induction machine. We'll next see the characteristic represent these are the two flags, two rotating flags. So the MF, can be calculated with this equation. Theta is different. Theta is clockwise, theta is anti-clockwise. And the flux can be explained, can be write in another one. So it's two rotational flux. And the direction is different. So this is the theorem of single machine, single phase induction machine. And here is some methods to start the induction machine. Maybe use resistance, inductance, capacitance. All can change the phase architecture. If the theta doesn't equal to 0, it will generate the starting torque. In most applications, we use the capacitor start motor. It's just
Capacitor.
here. This one capacitor. This one. And the starting first, we can close this switch. So there will generate a torque to make the motor rotating. After that, we'll open the switch. Then only the main winding is working. It can continue to work. So here we say there's a 19%, 19 degree phase shift. Generally, if it's not 19, maybe 100, maybe 80 or 60 degrees. Also it can rotate. But 19 degrees is better. So this is the starting. I started this. I wrote so the two current. There's the resultant current, and the source of which will generate the power with the torque. So let's see the curve, the torque speed curve. So the torque speed curve is this. First, here is the starting progress. after the starting progress, we open the switch, open the switch, here, we open this switch. After we open this switch, the curve will be changed to this one, and the top is different, but it can still rotate. So single phase induction machine. We just need to understand it. It's not the part of there's no a single induction machine on our textbook. There's no. So we just I let you understand it. It's okay.
Is also single induction.
Yeah, single. Yeah. But sometimes if they use this three phase, but this small
The small one.
smaller, so it's just a single phase source, single phase.
This is two motors. One is outside and one is
Yeah.
inside. So inside is DC.
No, is this it? No, AC.
The outside motor, outside this big motor is AC, but inside
Small.
is a small one.
It's small.
Is also AC.
So I think it's single phase, AC, AC single phase. Okay, let's see. Okay, this is. Okay, let's see. Just see a video. Use this. Which one? One is okay.
Single this one.
Single-phase induction motors require just one power phase for its operation. They are found in domestic as well as industrial use. Main components of single-phase motors are as follows. A rotor, which is the rotating part. A stator winding, which is stationary. It has got two parts, one main winding and one auxiliary winding. Auxiliary winding is placed perpendicular to the main winding. A capacitor is connected in auxiliary winding. Let's assume there is only one coil in main and auxiliary winding to understand its working better. Assume no current is flowing through auxiliary winding. AC current passing through main winding will produce a fluctuating magnetic field. Working a single-phase induction motor is simple. Just put one rotor, which is already rotating, inside such a magnetic field. You can note one interesting thing. The rotor will keep on rotating in the same direction. The reason is as follows. The fluctuating field is equivalent to sum of two oppositely rotating magnetic fields. This concept is known as double revolving field theory. Effect of rotating magnetic field on rotor is interesting. Since magnetic field is varying, electricity is induced in rotor bars due to electromagnetic induction. So here is a situation of current carrying bars are immersed in magnetic field. This will produce a force according to Lorentz law, so rotor will start rotating. But here we have got two such oppositely rotating magnetic fields, so torques produced by them will be equal and opposite. Net effect will be zero torque on rotor, so rotor won't start, it will simply buzz. But if we can somehow give this rotor an initial rotation, one torque will be greater than other.
Yes.
There will be a net torque in same direction of initial rotation. As a result, the loop will keep on rotating in the same direction. This is the way single-phase induction motors work. But one big problem remains. how to provide such an initial rotation. Nikola Tesla, a famous Yugoslav inventor, suggested one ingenious solution to this problem. If we can cancel any of the rotating fields, we will be able to start the motor. The auxiliary winding cum capacitor arrangement is used exactly for this purpose. Auxiliary winding also produces two oppositely revolving magnetic fields. One of them will cancel RMF of main winding and the other will get added up. The resultant will be a single magnetic field which revolves under specific speed. Such a magnetic field can give starting torque to the rotor, or the motor will self-start. After the rotor has attained a specific speed, even if you cut the auxiliary winding, it will keep on rotating as explained earlier. This cutting action is done through a centrifugal switch. That's all about working of.
Okay. That's two, but they are similar. So only one is okay. Okay, just let's see. This two is same. The two is similar. Just let's see one is okay. And complete. Okay, that's finished. Next week,